Okay, so I'm going to be talking about assuring non-deterministic software-based systems. My name is Dionisio Denis, that's the full name. I'm basically a principal researcher here at the SEI and lead of CPS ULS. So what exactly are we talking about here? The problem we are going after is the validation of systems that have non-deterministic behavior inside, right? So this non-deterministic behavior comes from, I would say, two main sources. One is the algorithm itself is non-deterministic, and the most popular today is machine learning, right? So we have an algorithm that actually is learning, so it's modifying its behavior as it executes, if you will. So obviously we have a problem with that. I mean, how do we verify a system that is not really defining its behavior at the same time? So we cannot do that, right? We need to have an alternative approach. The second thing is that whenever these systems work in the physical environment, like what we call a physical system, then the environment itself has a lot of non-deterministic behavior. Right? So this behavior also needs to be taken into account. And actually, this is actually what we are trying to go after. How do we deal with these two kind of non-deterministic factors here? What we do is we're trying to do two things, is try to go after effective techniques for verification of these systems and also engineering these systems to increase their usability, right? We will see two projects that will talk about these two elements. In particular, part of this, the objective that we have is to develop code that is trustworthy. We are going after verification. We are going about trusting the system. We are also trying to do this timely, meaning one of the elements or the characteristics of our research is trying to scale up the techniques that we have. And scaling up meaning we want to be able to do this faster. We are trying to do it more affordable. And this talks about applying this to large systems as well. And it means that we can incorporate more capabilities. And we will see when we incorporate more capabilities, the more capabilities we incorporate, the more risk we're going to be kind of taking, if you will. But we will kind of, we'll propose a particular scheme to go after those risks. In our case, we are going after both the state of the art and the state of the practice, improving both of them. We have some techniques that have been developed in the research communities. We're trying to apply them. And then during the application, we run into new challenges that we need to address. And those are the new kind of, I would say, state-of-the-art innovations, if you will. So two projects, basically. One is, the name is called What Will the Robot Do Next? This is basically a project based on, or the topic is human-machine teaming. And the idea is to say, how can we, as a human, working with a robot, really figure out what the robot will be doing such that I can trust what he is going to be doing. Clearly, if we have no clue what the robot will do, then we may not be very comfortable sitting next to the robot. So that comfort is beyond comfort, of course, is safety. But let's assume that the robot is very safe. But even if it's very safe, if we cannot trust the actions, it's actually counterproductive. So we are trying to go after that. And the second thing is called Certifiable Distributed Runtime Assurance. And it's a technique that where we actually take advantage of what Claire was saying. She was saying we can ignore things. We love to ignore things, right? We want to ignore everything except for a small piece of code that we add that is the enforcer. So it's a small piece of code that is added to the system, and this code will be watching the output of the system, and if it discovers that the output is incorrect, we will replace that with a correct action. In this case, the correctness goes after safety. So we will see what are the focus that we have a little bit later on when I discuss more details of the project. And clearly, this will have, I would say, much more, elements from previous projects that we have worked on. From the robot point of view, what did the robot, or why did the robot do that? We need to explain what the robot is doing. And from the Certifiable Runtime Assurance, we have a couple of projects. The most important one is distributed adaptive runtime systems. I'll point out to a few things that we are recovering from there. So let's start with the robot project, right? I am not the PI. Drew is the PI. I will explain the best, the summary that I have in my head. I can answer some questions, but probably Drew can answer additional ones if you have. Basically, as I was telling you, understanding the behavior of the robot is very important, right? Because we are now thinking about the robots actually will not do the, let's see, the mission by themselves. It's very common today to think about robots and humans working together. There are multiple, I would say, projects that are going after, because that's very important, very useful, right? But it is very important to understand, let's see, the challenge that we have, perhaps that's a better way to put it, is that the robot is, I would say, executing actions based on an algorithm that is a black box to the human, right? Typically, they will say the algorithm will try to do the best action possible. It will try to optimize the actions, but sometimes that optimization is not an obvious optimization that is in the human head, right? So that's going to be a big problem for us. So we need to find a way to communicate this. It means that part of this design, if you will, also needs to take into account not only the optimality, but if we are in a team, it also needs to be talking about or take into account, right, the actions, the understandability of the actions for the human, right? And I guess you can think of what we do while we drive. Sometimes we drive and do kind of maneuvers in a way that the other drivers will be able to understand us. And that's kind of part of the natural way we communicate. That is part of what this intuition is about, right? It's very interesting that there is we have metrics to measure how understandable this is and how much we trust a robot. And the metric that is very common in the community is called neglect tolerance. So it means for how long can I ignore the robot and still feel safe? I will ignore it. Maybe I can ignore it for 30 seconds, maybe 1 minute, maybe 5 minutes. The longer, the more trust kind of this is we are talking about, right? So this is something that has been kind of used in the past and by the community, and this is one of the metrics that has been used in this project. One of the interesting results here that is the one that I want to highlight about this project, so I will not discuss a lot about the project, is something that is the critical points, evaluating critical points in the trajectory. This is a paper that was published in an IEEE symposium. And the idea behind that is that this is a test on humans, not on robots. So there is an algorithm in the robot that will generate a trajectory based on a criteria. And then we are judging humans to say, can you understand what is the intention of the robot, right? So the intention in this case is very simple, and the idea of this simply is to be able to get to metrics, right? And we can see here that we have different, I would say, fields, let's call it fields, where we have two types of material, if you will. One is grass and the other is rock. So we can think of, okay, so if the robot has a preference for grass, then we expect him to move around the field in order trying to step on grass and avoiding rocks, right? And the idea of this trajectory is we have a starting point and an end point. And you can see here, for instance, it's very clear that it goes through grass only. But interestingly enough, because it's a trajectory that is kind of obvious, it's a straight line, we really do not know if there is a preference in the robot, right? So it's not clear to us. It only starts to make a sense that there is some preference when we start getting what is called an inflection point. The robot starts from here, and then it says, okay, I need to deviate. And you see the deviation is just about when it will be stepping on a rock. Right? So, well, maybe the idea is that he's trying to avoid rocks. Right? So then this was actually put in front of users using the mechanical Turk from Amazon. I think there was around 90 users. And there were a number of questions. Some of them were about how certain are you that you understand the behavior or the preference of the robot? For instance, what is, perhaps the other one that is interesting is they were asked to draw a line, the trajectory they think the robot will take. And then there is a cost on the inflection points and the compromise points. The compromise points are the ones that step on the material that is not the preference. Right? So there is a way to discount, let's see, the points because of that. So there was a way to get the cost of the robot trajectory and the cost of the user drone trajectory, and that was, we were able to get an index, if you will, right? So it was very interesting to convey, let's see, this preference and to find out what is the best action that the robot can take to convey a preference. Very specifically here, the action that was more significant was the inflection and not the compromise. If we have a compromise, there is less certainty from the user that there is a preference in the robot, right? So that was kind of part of the outputs of this research. We have collaborators from the Robotics Institute. A previous SEI employee was part of this project, now in Chatham University. And of course, I will try to answer questions if you have about that, but Drew will also, I guess we'll have more information about this. Let me jump into the next project. The next project is Certifiable Distributed Runtime Assurance. In this case, I am the PI. I will be able to answer most of the questions. Obviously, when I don't have an answer, it's because we are researching. We are figuring out that, and I will be very happy to get more input on that. So let's go back to what we were talking about before, right? So we are talking about having enforcers that will be added to the system. But the reason why we do this is because, first of all, traditional verification do not scale. Techniques like model checking that are very exhaustive. I guess in the past, Will, you were using static verification techniques in addition to perhaps model checking. So I mean, there are other techniques that can scale. We're trying to see whether we can apply exhaustive techniques to very large systems to get a guarantee on the whole behavior, but still make it scalable, right? The scalability is a big issue. The second thing is unpredictable algorithms. We were discussing this at the beginning, right? Machine learning. Today, verifying machine learning is a huge problem, right? So as I was saying before, I would say our trick is to say ignore. We love ignoring, right? So the more I ignore, the better I will be. Except for the fact that we will focus on specific properties and say, for those properties, we will put an enforcer. The enforcer will be watching the output. So you say, okay, I watch the output. You can imagine the example that we typically have, and we have demos for this, is a drone that is flying around, and it should stay within a virtual fence, right? So obviously what I'm trying to say is like, well, if the navigation software is trying to move the drone outside, the enforcer will stop that action and do an action that is safe, maybe just go back to the center. Very simple example, right? Clearly there are more complications, otherwise this will not be a project of this size. A very simple addition to this is to say, imagine that the unverified software is taking too long to respond, right? It's taking too long to kind of issue an output, maybe because it's in an infinite loop, right? If that is the case, then for that case, we have actually what we call the temporal enforcer. It means we have a timer that is actually ticking there, and as soon as we see it's getting too late, we will kick in and do a safe action, right? So we have the protection from both sides. Because it's a cyber physical system, the cyber physical system needs to be correct based on the output, the values of the output, and when the output is produced, right? The typical example is the airbag. If it doesn't play in 20 milliseconds, you hit the steering wheel. So all of these are the examples of cyber physical system. Of course, there are previous work. This this addition of enforcers comes, I guess, the initial work. Maybe there are previous work that this is coming from Simplex. Also, the Simplex architecture was developed by the SEI. It was developed by one of the researchers at the SEI and a professor at CMU. Actually, the professor, we are very fortunate now that Bruce has joined our team, so we are continuing very strongly in this area. And the idea or the focus at that time was control theoretic analysis. And I think this is very good, and it's kind of the basis of this kind of verification. But we also need to go after, well, if the code implementation is wrong, well, things will be wrong, right? So we go after that. We verify the code. And of course, if you do this at the wrong time, things will be wrong as well. So that's the second thing that we go after, right? The other kind of research project is from Claire Tomlin. It has been very well regarded nowadays. She called it a safe learning. And safe learning is about a control theoretic approach as well. There are some kind of way to have enforcers and verify these enforcers with hybrid verification. And finally, obviously, these kind of the lack of code and timing verification is also present or absent, I would say. The verification is absent in those two areas, so that's what we are going after. And finally, this was generalized into what is called runtime assurance. And that's why you see that title that we have is runtime assurance. So runtime assurance is to say the enforcer itself is doing some sort of an assurance because this is kind of preventing wrong outputs, right? But then if you verify the enforcer, then you get the whole verification, the whole system, right? And that's what we are going after. Most or a lot of these projects in runtime assurance goes after the logical verification. Some of them goes up after also temporal verification. In this case, is kind of a step before, if you will, that is just temporal sampling of the state, that if you don't do it at the right time, you can get in trouble as well. Right? So I will get into hopefully a high-level picture. I know there is some math here, so we don't need to look too much into that. The only thing we are trying to say is that we define all the different states the system can be in. If you can think of a robot, a drone, as we were talking about, so all the possible positions is all this, X and Y for now. There are more variables here, but let's ignore the other variables. X, Y, and you say, well, all the possible positions are all the possible states. We define what are the set of states that is safe. This is the virtual fence. And then we define a subset of that state that is that those states where I can take an action and prevent the system from getting outside this region, right? So that's what we call the enforceable state. There exists an action. There is an action that I can take to keep it within the enforceable state. And that is important because, for instance, once I get outside this enforceable state, like here, right, the inertia of the system will be such that I cannot prevent it in all occasions to kind of bring it back to safety. So we kind of deem this area like, forget it, we cannot do anything. So that's why it's not enforceable, right? So once we have that definition, there's a couple of things to think about. We define the transitions based on actions, and these actions are periodic. So we have a period that says this is defined based on the periodicity of the actions being enforced. So this is traditional mindset of control systems, right? So we have a control system, we sample the state, we do corrections in a timely fashion. So therefore we can prevent, for instance, crashes or getting into instability. Right? Did I move? Yeah. So the logical enforcer then is the one that will be watching. So this is a logical enforcer. It will be watching, and it has a collection of safe actions. So the logical enforcer will receive the action from the system, and will say, okay, let me look at this action. Does this action belong to the set of safe actions that I have based on the state that I am, right? So for instance, if I'm here, he will say, well, what are the actions that I have? In this case, I only have one that is safe, is enforceable. And I have other actions. This will take me to an unsafe state. This will take me to an unenforceable state. So this is my only action at this point in time. But there can be other actions, right? So that's actually what we do. We find out whether it belongs to the set of safe actions. If it belongs to the safe actions, we don't do anything. Let it pass. It's safe. But if it doesn't, then we pick one from these safe actions, right? And that also allows us to actually do composition that we will not discuss much here today. But if we apply this directly to the drone, just a few observations, we talk about the XY. That was the position of the drone, right? We talk about the safe state is staying within this region. This is a rectangle now, just for simplicity. We add also the direction of the drone is an angle. Where are we flying and at a constant velocity? This is a very simple way to express the state space. And then when we talk about the enforceable state is the state where I have kind of bounds to say, what is the farthest the drone can fly if I disregard any corrective action? And what is the farthest if I'm braking against kind of an unsafe action or movement, right? So we use that to define the enforceable state. Right? We don't need to look at this, to be honest. And then, of course, one of the things we wanted to do is to compose enforcers. What if we have multiple enforcers, right? At this point in time, we have a very simple way to handle this composition. For instance, one enforcer can be trying to prevent the drone from flying outside the fence, and another is trying to keep a minimum distance between the two. Obviously, if these drones keep moving closer and closer to this one, it will reach a point where it cannot, I would say, sustain both properties, right? Either it will need to get outside of the fence to keep minimal distance, or it will need to violate the minimal distance. So then we use priority in this case. It's a very simple way to do it. But in the future, we are thinking of more complex resolutions of conflict, right? Trying to do a look ahead to find out whether we can see that we will get into a situation like that and we can avoid that situation, right? And then the question is like, okay, so that's good. Are we done? Well, actually, no, because the problem, as we described before, is, well, what if we get into an infinite loop? We have a problem, right? All of that theory was assuming that we can do periodic actuations. But what if we get delay and we go beyond the period? So we need to go after that, right? So there are two ideas behind this. Probably it's going to be easier to express this in a diagram. I will go for a diagram. But typically what we do in a processor, and we are trying to schedule to ensure that all the tasks will be executed periodically, is we will have a CPU, and the scheduler will decide who runs first and who goes next. For instance, if all of these tasks we have high, medium, and low priority arrive at the same time, we need to decide who will run first. So for instance, we will decide in this case, this is fixed priority, that the highest task will run first. That's by definition priority scheduling. And then in this case, we will do sensing, compute an actuation, and send the actuation. And obviously, what we want to do is finish before the next arrival, the next periodic activation, right? Then once we are done with this, we will go for the second priority, right? It will start executing, and then at that point in time, it may have a second arrival of the high priority. So it means we need to wait for this it will preempt us, continue the execution, and maybe after that we will be able to finish, right? Obviously, we need to ensure that this response time needs to be shorter than the period. And after we are done with that, maybe we will let this guy execute now, which can have additional preemptions, and it will get a larger response time. So for all of these, there are some math to calculate this response time, and that will ensure that the response time will be within the period, as the assumption that we had before was required. But of course, there are problems. What if we run into this very long execution, right? If the high priority task gets into a very long execution, this guy will keep running and running and running, and multiple errors will happen. One is that it will be missing deadlines. We should be seeing outputs every period, right? And we are not seeing that. There are multiple periods without outputs, and we get an output here, but the output is actually late in both ways, the output, the actuation, and also it was calculated with very old sensing data, right? And this kind of a long execution also will prevent these guys from finishing, both of them, right? So what can we do? What we add is to have budget enforcers. So it means each of them will have only a specific budget where they can run. So for instance, in this case, if he's trying to go beyond the budget, he will be paused, and then it will be resumed in the next period. So this will allow me to allow all the other tasks to finish on time. But we still have the problem of this old execution. So the sensing data was happening in this period, and the output is in the other period. So we solved one problem, but not the other one. So what we'll do is we'll say, okay, if we are running too late, we will add our own action. This is the timer that I was discussing before. Therefore, this will allow us now to have correct actions at the right time, right? We will get into other problems, right? Are we done yet? We are not done yet. Clearly, the other problem is that, well, we have bogus software running in our system. What is the bogus system? Gets into the memory of the software that we trust, right? Clearly, this can also be not only a bug, but can be an attack, a cyber attack. So can we do something about that, right? We are also relying on unverified kernel, unverified OS, unverified libraries. So what can we do? So what we can do is what we call a mixed trust computing. We identify pieces of code that we trust and pieces of code that we don't trust. If we go back to the original formulation, well, we have an enforcer, and we are trusting the enforcer, right? So the enforcer is a piece of code that we trust because it's verified. And the rest of the system is not verified, so we don't trust it. So what we do is we divide, let's see, this into two types of components, trusted and untrusted, and we create an infrastructure to protect the trusted components from the untrusted, to prevent this kind of breaches, if you will, right? And what we do for that is we use a proven micro-hypervisor. I don't know if you already have the talk of secure IoT. That's the same hypervisor we are using here. But in this case, we had to do an implementation of a scheduler inside the hypervisor that is going to ensure that the timing will be correct, right? So now, in this hypervisor, this is a very small hypervisor that focuses on protection. It's trusted because it's verified, so we will add these hyper apps that are trusted as well. And the idea here is that all these untrusted parts are here, the trusted parts, and the enforcer is here. And of course, one of the observations that I need to make is that if the untrusted part, I will say, well, the only thing that we can ensure is that the trusted part needs to be finished on time, and that's the only one we can trust that it will finish on time. This part we wouldn't know if it's kind of finished on time because the whole thing can die, right? I was telling you before that we have this piece of code that will check the output. We call it the logical enforcer. So this logical enforcer will still have it there in case that we are able to finish the computation. But if that is not able to finish, then this temporal enforcer will be in the hypervisor. But that requires then a new scheduler. Remember we were talking about this budget enforcement and how to ensure that the timing will be correct. So what we do now is we divide the task in what is called a mixed trust task. One piece of the task will be running the untrusted part with all the support of an OS, full OS, and only this temporal enforcer will be migrated into the hypervisor, right? In such a way that if for some reason the whole virtual machine dies, safety is still preserved because the virtual machine will be able to continue doing the proper actuations to keep the system safe, right? And that's kind of the whole point of saying, let's divide this into two pieces, right? We have tested this. We have an implementation, of course. It's very cool to kill the virtual machine and seeing things still working. Now, caveat here, of course, is that it's working only the safety part. Part of this kind of observation, maybe I will get into that. Let me do that observation here and we'll refresh that later, is that the reason why we need an untrusted part is because the untrusted computing, the untrusted software is very rich. It will have a lot of features. It will actually, we can use kind of open source community software because it's protected. As soon as we protect the safety with the enforcers, things will be fine. But of course, you can run into a situation that you have a drone, the drone is flying, and it's so safe that it doesn't move, right? Clearly, there is a problem there, right? So there is a trade-off, and we are going after that trade-off to say, how do we ensure that, right? But at the same time, we are able to take advantage of these advanced techniques, machine learning included, right? To say, we enable that We know they are unsafe, but most of the time it gives me a very good answer. So only watch the safety and things will be fine. That's the idea behind it, right? So this combination of two pieces of the task and the scheduling is what we call the mixed trust scheduling. And we combine and synchronize two schedulers. One is in the virtual machine and the other is in the hypervisor. These are just, it's fixed priority as I was presenting before. This is preemptive, so you will see the preemptions that I show in the graph. And this is non-preemptive, this just simplifies verification. We can discuss it later. I guess we will not have a lot of time, but I can address that in the questions. And of course, that requires new verification equations. I haven't shown those equations, but we can look at them if you want. Again, a few remarks of the mixed trust computing. The idea is to say we want to apply strong verification techniques to very small code, right? So you saw that we even go all the way down to the hypervisor. So we are taking advantage of these UberXMSF, it's very difficult for me to pronounce that, that is verified. It's not only verified, but it also has a verification framework for compositionality that allows you to add hypertask and to have a verification on top of the hypertask, to apply verification to the hypertask. But that also talks about that when we go into the logical enforcer, as we discussed before, we also applied very strong verification techniques there, right? So in this particular case, just to give you the flavor of the verification, we are using a tool called Pharmacy, and Pharmacy takes C code, and from the C code, you add, I will say, logical propositions, and you will check those conditions to see whether they are true or not, right? And that's the idea going after that. Clearly, one of the things that we are very excited about, there are multiple things. One is that reducing the code gives us speed. This could be really fast, hopefully, if we are able to reach the properties that we want, right? So this is part of the exploration. Second, of course, it's cheaper, because it's faster, it's cheaper as well. We can actually take advantage of open source code, for instance. We can go and search the internet, or let me put this here. As soon as you have the enforcer, it will watch it to say, well, never violate these conditions, and it will kind of go after that, of course. The sad part is that sometimes it will be violating so much the conditions that it may not work at all, but we will still be safe. Let me see if I'm missing something. I think those are the main points, right? We have multiple outcomes. We have schedulers, that is code that is running in particular platforms. We have a code that is running in Raspberry Pi 3. We have, of course, applications demos. We have verification algorithms to do the scheduling and to do the verification of the logical verification. We have a drone laboratory and demos there. Typically, one of the things that has happened recently is that in the demos, there are multiple components. We added a serial driver inside the hypervisor in order to do safe communication. And this serial driver is buggy. Clearly, we have not verified that. It's experimental. So while we are not certain about this, the safety of this driver, we are experimenting with simulations of drones instead of the real drones. And once we have something comfortable, then we will go outside and fly it. But that's kind of a situation. Always, verification is as good as the assumptions, right? Are we done yet? Not really, right? The idea is to say we are very happy with what we have today, but this challenge to say how do we ensure that we really achieve the mission, we achieve the mission performance that we want, right? Can we be sure that we are not too safe? There is a talk from Mobileye that talks about the challenge of autonomous driving, and there are some very nice videos, probably I should have included some of these videos here, that talks about the need of these autonomous cars to be aggressive. And he presents some experiments in driving through Jerusalem, and say, if you are not aggressive, you basically block the roads. And it's actually way more dangerous than being aggressive. And there are a lot of techniques, very nice discussion. So that is a challenge for us. I mean, we need to push that envelope and find out what is the level of aggressiveness we need to go after, right? We have, for instance, the composition that we have today is simple. We are now trying to apply more complex verification or the relaxation techniques, I will say. There is a new technique called MaxSat. And we're trying to find out whether you can apply that to relax some of the assumptions when we put multiple enforcers together and see what is the effect on the system-wide, right? And of course, all these trade-offs between mission performance and safety, right? This is our team. I was talking about Professor Bruce Kroc that joined our team. Amit is our genius in research, of course. And I mean, you can see professors from CMU. We have a very long, I would say, collaboration with Professor John Lechowski in the real-time area. We are very happy with the group. Right? And I think that's it. This is the two of us. If you have questions, I'll be happy to answer. Oh, one question. Okay. Okay, one. Good. We can talk outside as well, so that's fine.
I just wanted to know the limits of the assumptions that you make. If you're verifying things you're verifying things at the model level, and then you have, I think you said, a verified compiler, but at the lowest levels, do you have a verified assembler? And
yes.
Yeah, where does that stop being verified?
Actually, it's going to be more surprising, my answer, I think. So, for instance, when we talk about the hypervisor has a definition of the hardware from where all the assumptions are set, the hardware, the instruction set, right? All the assumptions are set up there, and we define each of the instructions in the instruction set to find out what is the floor. That's the floor. On top of that, you have certified compilers, so that is used. And on top of that, you have these tools that is the FRAMA-C that will actually do this verification all the way down, right? So we are able to do that for the logical verification side, the protection that the hypervisor is using. From the timing point of view, we have a mixed bag at this point in time. The mixed bag is with respect to, we have all the equations that prove that things are correct. These equations, but we do not have, for these particular equations, the proof that the code is implementing the equations correctly. We have a previous proof for previous equations where we prove that the code was implementing the equations correctly. So we have that, we just need to redo what we have before in order to get there. Now, this is now the bad news. The bad news is that so far, it's kind of bad and good. So far, we make very simple assumptions about the physics. Our physics model is a little bit weak. It's very conservative, our system, and if we get into some funny behavior of the propellers, for instance, then things will be voided. The good thing is that now we have way more support for the physics with Professor Kroc coming to our team. He's already producing, I think, 3 papers in the very short period he has been with us, helping us push this envelope. But there is always let's see, let me think how to say it. We need to be very careful about how the model of the physics reflects the reality. So there is some level of fidelity that we need to be attentive, if you will. That is something we don't, I will say, I will put it on the table, but we don't have really a clear answer yet.
Okay, thank you, Gio.
Yeah.